kids, for section 1.1, we're going to just kind of breeze through some of these examples. Okay, so for example 1, the only thing I really want you to take from this, don't worry about all the details on this, but if we have an interval that's written like this is the same thing as saying x is in between 3 and 4, and since it's brackets like this, we have equal to lines under those inequalities. So that's really all I want you to take from that. If we had something like this, it would be x is in between 5 and 10, and since those are parentheses, we don't have the equal to lines underneath the inequalities. So once again, example 1 and example 2, that's the extent that I want you to understand that. So moving on to example 3, we'll actually go through this one. It says find the roots and sketch the graph of f of x equals x cubed minus 2x. So the first thing is finding the roots, or setting this equal to 0 and solving for x. So to solve for x, it's easiest if we factor out an x. Then we can use the zero product property, and we can say this piece times this piece is equal to 0. So that means x is equal to 0, as well as x squared minus 2 is equal to 0. So that's one of our roots. From here, we just continue solving using algebra, square root both sides. And when you introduce a square root into an algebra problem, you need to do plus or minus. Okay, so we have 3 roots. We have 0, positive square root of 2, and the negative square root of 2. And so if we're going to graph this, we're just going to look at those. So we're going to say there's a 0 here. We know there's negative square root of 2 over here. We know there's positive square root of 2 right here. And so these are the 3 places it's going to cross the x-axis. Now if we look at the original function, it's a third degree function, third degree polynomial, and if it's positive, like out here, so if we have like a positive number and then x cubed, it's going to look like this. If we have a negative number and it's x cubed, it's going to look like this. So since we have this situation, we're just going to sketch it, and we see that it's going to look something like that. And that's our sketch for that one. Now, an alternative thing that we could do, we could plug in values for x and then plot them. That takes a lot longer, but feel free to do it. Your book shows that method, so if you're interested in that, you can do that, or you can ask me in class and I can go through that method. Now we're going to move on to example 4. And it says determine whether the function is even, odd, or neither. And to do that, I'm going to write all 3 of these down. Okay, if you have access to a graphing calculator, that's probably the easiest. So I'm just going to show you some definitions. So even if we're looking at it visually, it's going to be something that's symmetric about the y-axis. Now that's what this is gonna be. Odd is something that's symmetric about the origin, which what that means is if we took this piece and we reflected it over here, and then if we took it and reflected it down here again. So it's like we take a piece, reflect it across the x and then the y, or we could reflect it across the y and then the x, and if that lines up, then we call that an odd function. And then neither is just anything that doesn't fit those 2 definitions. Now, more formally, if we plug in a negative x to a function and we get the original function we're going to call that even. And if we plug in a negative x and we get the opposite of the original function, that's going to be odd. Okay, so I'm going to go through these with this definition written in white. So what I do, so if I'm doing this one up here, I plug in a negative x, and if we do negative x times itself 4 times, we end up with just x to the 4th, and since that's exactly the same, we're going to call this one even. Now I'm going to do this one. So I have x to the negative 1, but I'm plugging in a negative 1. Now for me, it's a little bit easier not to deal with the negative exponent. So the first thing I'm going to do is just transform it into this. And I get negative 1 over x. And that is, this one can be written as 1 over x. And so if we compare that to that, we see that it's exactly opposite. And so that fits our definition of odd. And this last one, we're going to plug in negative x squared and negative x. Negative x times negative x gives us x squared minus x. And we see that this sign right here didn't change, but this sign right here did change. So some of it changed, some of it didn't. So it's not exactly opposite. It's not exactly the same. And so we're going to call that one neither.